matters about timelines is that they represent both events happening at specific points in time and aggregates that continue until change. When we were working on a lot of different feature engineering tasks, this came up a lot, needing to kind of represent aggregations and interpolate at different points. So we say that events are discrete timelines because they represent specific points in time. For example, purchase events received from a student. Unlike a typical time series, the points in the timeline don't occur with like a fixed frequency. So we see here purchase events happen whenever the user makes a purchase. Aggregations over a timeline produce a cumulative value, the result up to and including each time. We say that aggregations are continuous timelines because the value continues until the next change. So it makes graphs that look kind of like a step line where it continues and then it jumps up when a new purchase happens. The second assumption that I mentioned in the beginning is that values are naturally grouped by entity. So when looking at purchases, it's natural to associate the purchases with the user making the purchase. Depending on the query, we may need to reassociate events with other entities, the store or item being purchased. Conceptually, picture separate points or lines on the timeline for each entity, kind of like we're showing here. So timelines make these two assumptions, ordering and grouping. But these aren't very limited. In fact, these assumptions are almost always applicable to events. For instance, events in a Kafka stream are ordered, and they're grouped by the stream implementation itself. The benefit is that timelines apply all the way down when working with events. Input events and facts can be treated as equivalent timelines. The timeline abstraction retains the value and temporal information from the input without any loss. Queries operate on timelines. Each operation that we're going to see later takes one or more timelines and produces a timeline. Finally, the resulting timeline is output to a stream or table. There are two ways a timeline may be output, as the complete history or as a snapshot at a point in time, which is critical for some of the ML use cases we've looked at. Looking a little bit further at what we mean by these two kinds of output, or these two views. The timeline history contains all of the points in that timeline. So here we see every time the sum changes, we see an event saying which user the value changed for, when it changed, and what it changed to. So this representation is useful for visualizing the times or the values over time, as well as for producing training examples from the past. In a lot of our predictive cases, we aren't trying to predict just values now from features now. We're trying to say, based on what we knew 2 months ago, what is the value now? The other way we can look at them is as a snapshot. So we can say, take a point in time. Often this is the latest point in time, but it could be any point. And just give us a view of the value for each entity at that time. This might be useful for populating a dashboard or for populating an ML feature store that you can then serve those feature values for and make predictions. Both continuous and discrete timelines support history and snapshot views, and composing a query is independent of this output choice. So you can write your query without having to worry about whether or not you need the history or snapshots, which we find very useful because it lets us write a feature and then export it as the history for creating training examples and export it as a snapshot for feature survey. Kind of wrapping up on timelines, I started saying abstractions matter. Kaskada is built on timelines. Timelines make those two simple assumptions, ordering and grouping, which makes them natural for events. If you're working with temporal data, you're likely already thinking in terms of timelines, and you should be writing your queries using them too. Looking at some simple queries to kind of see the benefits, we're going to work with these three different streams of events in this kind of e-commerce setting. So purchases, page views, and reviews. First, we'll ask, how much did each user spending change over time? This suggests we want some kind of cumulative aggregation. So visually, we have a discrete timeline of purchases. That's what we're starting with. And each time a purchase occurs, we want the sum to change. The corresponding query using timelines matches this idea. We just compute the sum of the purchased amounts. All aggregations on timelines are cumulative, which ensures that the result is a timeline and can then be used further. The second question is largely the same, but this time we want the sum within each month. When a new month starts, the aggregations are reset as if no purchases have occurred. We'll see how we can do a cumulative aggregation like this in SQL in a minute. But it's interesting to note here that unlike in SQL, which would just not have a row for a user that had no activity in a month, with the timeline we can clearly see like the value drops to 0, which is important for downstream systems that might otherwise remember the value from last month. Again, we see that the query matches this picture in our head. We want to perform a cumulative aggregation since the start of each month. Since timelines have an inherent idea of time, time-based windowing is straightforward. The third question is about the average number of page views between purchases. Deconstructing this, we'll want to use a mean aggregation, but we want to do it to a timeline containing the number of page views between purchases. So as a place to start, we'll count the page views since the previous purchase. We've already seen how to do that using the count or sum aggregation. This uses the same windowing we just saw. We reset at each purchase. The interesting thing to note here is that we previously used it with time, resetting once a month, and here we're resetting whenever a purchase happens. So it's easy to do time-based windows or database windows. But you'll note that this timeline that we have for the page view since purchase has points for every page view, but we wanted just the number of page views between purchases. So to do this, we will observe the timeline when a purchase happens. This kind of filters it out, so we only get one value, which is the total number of page views since the last purchase, when we make a purchase. Finally, we have the page views between purchases, and we just need to compute the average. Because the result so far is a timeline, we can just apply an aggregation to produce the answer. So looking at the query, it matches our original intuition, and it matches what we just did visually. We count the page views since the last purchase, we observe that when a purchase happens, and we take the average of those values. Since everything takes timelines and produces timelines, we can easily compose things. We can even do nested aggregations like this very easily. The final question we'll look at briefly is for the average product review at the time of purchase. Breaking this down, it seems like there should be two steps. First, compute the cumulative average review score for each product. Then join that with each user purchase. The tricky part is that we want to do it at the time of the purchase, not just a general join. So for the first part, we don't have item reviews, but remember they were keyed by user. So we'll need to use this with key function, or with the key operation, to kind of reorganize them or regroup them based on the item being reviewed. And then we can simply perform the mean. For the second part, the lookup or the join, we're going to take that value we just computed, the average score by items, and we're going to join that with the purchases, or with the item being purchased. So each time I purchase an item, I'm going to look up the corresponding value from the average scores by item, and that's going to be the result. So the interesting thing here is that it makes it easy to do point in time or as of joins. So timelines, we said are a natural abstraction for temporal values. They're also the natural result for temporal questions, which is what made it so easy for us to compose these queries, asking relatively sophisticated temporal questions. To understand the benefit of timelines and the two assumptions they made, let's quickly compare to SQL. So remember that we said there's two kinds of results, historic and snapshots, or point in time. And the first question was for the sum of purchases grouped by user. With timelines, we didn't need to think about whether or not we wanted the history or the snapshot. But with SQL, we have to write a different query. We have to do a cumulative sum in one case or a globally grouped sum in the other. That's not too bad, but timelines let you write the query once and create training examples or features for survey. For time-winded aggregations, starting to get a little trickier. We need a partition by both the user and the month. Doing this like trick lets us produce a value since the beginning of the month. Now note here that if the user has no activity in a month, you'll just get no result for them. One of the things that we've seen is that if you're like writing the changes to some downstream system, that can lead to like the previous month's value continuing in your feature survey. For the snapshot case, we don't need to use that trick. Instead, we can use a subquery to compute the current month and filter to that. But moving on to some of the larger queries, so for instance, this was the average number of page views between purchases. It's starting to get a little tricky, and I'm going to be honest, I didn't actually write this. I asked ChatGPT to do that, and then fixed a bug or two. And I won't really try to explain it in detail, but I'll just kind of note roughly what it has to do. In this first common table expression, it's trying to union these two different types of events. In order to do that, it has to use additional subqueries to kind of get the same columns or the same schema. And then in the third common table expression, we're going to use the same trick we just saw, but this time, because we're doing data-dependent windows, we have to first compute the window we want. So in this case, how many purchases have happened so far? So we already are starting to see, like, timelines made it a lot easier to work with multiple streams, and because operations take and return timelines, it's a lot easier to compose. For this last one, let's look at doing the temporal join for the just the snapshot case. Like, I have to thank ChatGPT for making this one come out. There's a trick this time is that we're going to compute the cumulative average review score at the time of each review. So this happens in the first common table expression. Then the second, third, and fourth common table expressions are trying to make this like lookup table that says, for a time, what is the most recent review that happened before that? And then in the final query, you can say, okay, at a given time, use that lookup table to figure out the most recent review, and then use the cumulative average review score at that time as the result. I would not have come up with that. But with all these tricks, it can be hard to know which ones to use for which questions, and which ones will be fastest in which scenarios. All these tricks are why even simple temporal queries are difficult in SQL. As a larger example, we took a Databricks example notebook for Churn using Spark SQL. 63 pages of SQL queries and plenty of tricks became 2 pages using timelines. Abstractions matter, and temporal queries may be written using SQL is a lot less natural than operating on timelines. It often requires finding new tricks or changing the question to use tricks you already know. But if the abstraction doesn't fit the question, you should change the abstraction, not the question. So let's briefly finish by talking a bit about Kaskada. If timelines are the way to express temporal questions, then Kaskada is how you answer those questions. Kaskada is an open source implementation of timelines. Execution is efficient thanks to columnar computation and taking heavy advantage of the ordering and grouping assumptions we talked about. It supports millions of events per second on my laptop, so you can get started without any special hardware or setting up a cluster. And Kaskada enables you to answer temporal questions today. We are working to build an inclusive and vibrant open source community. If you're interested in these kinds of problems, come talk to us. This has some of the places you can reach us. If you have temporal questions, give us a try and let us know how it goes. I'm here. There's a few people in the back here too. Come talk to one of us. We'd be happy to talk to you here or online.
We have a few minutes for the Q&A.
If you have any questions?
Yeah, go ahead.
Well, so here you use time as just sort of a continuous measure, but just as you can, for example, integrate over time, you can integrate over distance. So you can see that the same kind of tools that you use for time that make these queries more useful can be used for other metrics, like for example, displacement, right? Mm-hmm. So would it be easy to use what you have already for something else, or maybe extend it for that?
Interesting. So we've definitely thought about kind of changing from time to just some ordered quantity. I'm not sure how well kind of the operations on time would apply to kind of operations on displacement. It might be possible. Yeah.
Okay, I mean, it's just a simple thing because you can, just as you can have a window of time, you can have a window of space, and that would make certain things easier.
That makes sense. Yeah, that's an interesting idea.
Can I do aggregation?
I'm going to give an example. If I want to know how many weeks has it been since the player has played 3 activities.
So I think the question was looking at how many weeks has it been since the player played 3 activities? Let's see. Depending on if you want it to be since the player played at least 3 activities or like exactly 3 activities. Yeah, that would be pretty straightforward. You would create a discrete timeline, which is like, has the user played 3 events, which you can do with like count of the number of activities greater than 3. So that would be a discrete timeline that has like true points whenever that happened. And then you would say, just like time since that. You can take the time of that and subtract the current time. Yep.
Any other questions? Hello?
Okay, so I'm just wondering, with your windowed feature, I'm wondering if you have the ability to create sliding windows. I heard about the month definition, but I'm wondering about sliding, and I'm also wondering if there's a replay or a comparative ability, time over time.
So there's, so we do have sliding windows. You can basically ask for some multiple of the current measure, as well as I think there's some work in progress if you like on monthly windows sliding daily. I think, so then the replay question, was that kind of like writing a feature that's like the previous score versus this score, most recent score? Yeah, so one of the operations is lag, so you can basically say, I want this event from 3 or 1 occurrence ago, so you can look a little bit in the past. Yep.
All right, do we have maybe the last question? Okay.
So I'm just kind of curious. Yeah, sure. So have you run this in terms of like, I guess on like a multi-node setup, or is everything usually on one node? Or like, how does this look when you scale it out to like handle larger amounts of?
Yeah, so I mean, most of our execution right now has been on one node. As I said, we can kind of go to tens of millions of events per second on one machine. Largely, passing stuff around in memory is a lot more efficient than kind of distributed deployment. We are working on distributed deployments. And in fact, the way that we execute kind of on one machine on multiple threads is very similar to executing on multiple machines. So we have reason to believe that that's going to work well.
All right, great, thanks a lot.